So welcome everyone. This is the last section of this symposium. Our next speaker is Roger Hernandez from University of Sinaloa. Roger got his PhD from Sinvestav in Mexico. Then he moved to a research position in Buenos Aires, Argentina, and then to Valencia, Spain. So Roger, you have 40 minutes for your talk plus 5 minutes for questions. So please welcome to Roger.
Thank you. Thank you very much to everybody. First of all, I would like to, as the previous speakers, I would like to thank the organizers and also to congratulate the people from Puebla who is having this new center for science, and congratulations to Humberto, to Lorenzo, that I know that they are doing a lot of efforts to bring science to the physics community and the community, interdisciplinary in the area. So I'm going to talk this today about the amplitudes, divergences, and their precise predictions at for collider physics at the LHC, basically. So what I'm going to talk to you about is something related with what the previous speakers was giving very nice introduction and very nice overviews of their fields. And they were speaking mostly in quantum gravity and classical field theory. But I am trying to go into a different direction, which is collider physics. So first of all, we like to say that so in order to describe the physics of the collisions, the high energy collisions, we use quantum field theory, which relies on the unitary local quantum field theories. So as the previous speaker was pointing out, so the most problematic things are the computation of multi-loop scattering amplitudes. And if in our field, so these loop amplitudes will be the correction, the quantum corrections to the scattering processes. And these quantum corrections nowadays are the main bottlenecks on the amplitudes for the LHC. However, the people tend to say, well, we have to compute them, but they are also very hard to compute. But the LHC is working, and this is a very motivating subject, because they are computing, they are calculating observables, and they are pushing the boundaries of the precision frontier in experimental high energy physics, and we have to do something from the theoretical side. So this is a review of this is from 2000, and this was last month. They give us this very overview of the measurements of the total cross sections, measurements on the standard model. You can see that the theoretical prediction are also these gray bands. And also the experimental results are also very tiny. You can see that also they have the error bars, the bands, and the experiments are doing very good. Also the theory are doing very good. However, there is not the full channels that they are measuring. They're measuring a lot of different observables. And they are trying to understand not only the measurement, but also to say something about nature. And in order to do that, they need to compare the theoretical predictions with their experimental results. So this is the let's say the state of the art from the experimental side. What is the theoretical prediction? What are the most accurate theoretical prediction that we have nowadays? So as the previous speaker was saying, so we call it this next to leading order, next to, etc. And so the first theoretical prediction was in the 90s, when Van Nerven computed the Drell-Yan, and you can see that it has passed like so for the Higgs, you see that here in 2012 they started to the 2-photon channel, which was the main channel at the LHC. Then it has happened like it has three photons here in 2020, after 10 years more or less, they finished the next to leading order, but one extra particle. So it is difficult, but I would like to convince you why it's so difficult to compute these observables in this talk. But the previous speaker on the math on the first talk, he said that this is not the last computation at the highest position. So we have the frontier at next to leading order and to the cube leading order, and you see that they started to compute in 2014, more or less. The first computation, it was in 2014, and but the first next to leading order was in 1990. So most of like 15 years before the first computation of next to leading order. And now they have a different situation. I mean, once you know how to compute something, you try to compute other observables in order to give some more theoretical predictions. So what are the theoretical issues? Why they take too long to compute this cross-section, these numbers? First of all, the integrants that previous speakers were already saying. So the integrals, usually they are very lengthy. Also, I think it was, the first speaker too, Matt, was saying the number of Feynman diagrams increases enormously. When you ask for high accuracy, the number of Feynman diagrams, they tend to explode. But the most problematic things are the divergences. When you increase the number of Feynman diagrams, you are going to increase the number of divergences. The kind of divergences are going to, you have to deal with them, and you have to cancel all of them in order to produce some real numbers, because cross sections are real numbers. They don't have infinities. They don't have divergences. And also when you say, okay, I understand the behavior of the amplitudes. You know what are the divergences, where are located in the phase space or whatever. You need, in order to compare with the experimental results, you need to pass through a Monte Carlo simulation. You need to do some simulation of the interactions, and these simulations are given by these Monte Carlos programs. So if you have an instability in a Monte Carlo, it will take very, very long time to converge to the real number that you are trying to get. So it is hard because of that. Also, another important thing is that, okay, you need these corrections, but also you have to think in mind, or having in mind, that you from time to time, you are going to, the experimental colleagues are going to ask you for more accurate results, more accurate theoretical predictions. So, and moreover, if you think on the new physics program, new physics projects are always tends to say that the nature is going to pop up from small deviations, and this small deviation has to be under control. So if you see, for instance, these bands, so you have the next to leading order in light green, so the errors are very well understood, but there is also large corrections here. But if you go to the next to leading order plus next to leading log computations, so the errors are shifted, they are moved into another direction. So there is not, you could say also, maybe there are some physics, new physics, if you compute this number. I mean, I don't know if you see the pointer, but if you look at some numbers, and when you measure it, you don't measure the right thing. Maybe you are overestimating or underestimated the result, because you need to compute higher order corrections. So it is important to.
Roger,
yes.
Can I ask you something before you move to the next
yes.
slide? So
yes.
Regarding the Monte Carlo simulation, so the calculations that they do using Monte Carlo simulation are as accurate, or they are more precise than the theoretical predictions.
they need to, I mean, they for instance, in here in this plot, they need to have the kernels, and the kernels have to be canceling all the divergences inside. So that's the problem. So if you know all the kernels from the real and the virtual and everything, and if all the cancellation takes place locally, then it will be simpler for the Monte Carlo to be done. But that is the issue, because as you know, you have several diagrams, you have several singularities, and that is the problem to compute the kernels.
I see. And what about lattice QCD? Can be lattice QCD be used to cure some of those problems, or it has the same problems as Monte Carlo? Or Monte Carlo is lattice QCD?
No. Monte Carlo for us is like when you do this perturbative QCD, and lattice, they try to discretize the space-time and do these integrals, but there are some different approaches.
How lattice compare with like lattice? Say we don't have smart people in our field to propose new methods. We could say, oh, we can just use lattice QCD, and lattice QCD will be good enough. That would be something to say.
Maybe I am not. I'm going to say something naive. I know that, for instance, lattice QCD can extract the parameters of the Lagrangian, for instance, the masses and some couplings. I don't know how it's going to translate, for instance, into the cross-section level.
Oh,
I mean, I know I don't see how. Maybe I am not the one to ask this kind of question, but as far as I understand, they can compute, for instance, I don't know, the form factors or of parameters in a very precise way. They don't pass through all this Feynman diagrammatic approach.
I see. All right. Yeah, that answered my question. Thanks a lot.
No, thanks to you. And as previous speakers, if you have questions, you just raise, well, don't raise the hand because I don't see them. just speak aloud, and then we try to figure out what to do. So then, yes, so this is the bottleneck that we have. We need to compute amplitudes, and these amplitudes has divergences. But the problem is that when you pass through a Monte Carlo, so the Monte Carlo has to take care of all these instabilities, numerical instabilities, in order to converge into the real numbers. That is the problem here. And then you have to add leading log correction and everything. So how do we handle infinities for us? So first, we need to compute in the way that quantum fields perturbatively, we can compute something in quantum field theory. What we do is you use the Feynman rules, as Andres was saying. I see a diagram and I see a Feynman rule there. So then you have to provide your set of Feynman rules, and once you have these Feynman rules, you can compute what we call it the scattering amplitude, the amplitude. Then you square it, and then it is proportional. Then you, like a quantum system, and you have to have or to take care of all the possibilities of the phase space. So the integral of the phase space of the Feynman of the scattering amplitude, and the scattering amplitude is made of Feynman diagrams. So what is the problem? The problem is that you are extrapolating the quantum field theory to two regions which are problematic. To the infinity region, when you have loop integrals, and when you have a zero energy, infinity energy, sorry, and the zero energy. And the zero energy is when parallel particles are produced parallel, when they mimic the behavior of one single particle. As an experimentalist, if you ask for an experimentalist, can you see you have an infinite resolution? So it would tell you, of course not, I don't have any infinite resolution, but theoretically you can draw a line and you can separate two tracks, but in experimental area it is not possible. So this configuration is going to blow up the amplitude. So how do you take care of that? Then you have to consider, as the other speaker said, you have to add a real correction in order to cancel some divergences there. Now, the problem is that sometimes there are these two regions, so the zero limit, so zero energy, and and the infinity when you have an infinity energy. But there are other divergences that appear by chance, because sometimes the denominators, they could have some random numbers, and in between these random numbers, they can produce singularities. And these are the so-called threshold singularities. So basically, you have three singularities. You have the ultraviolet with the high energy limit, you have the infrared with the low energy limit, and you have threshold singularities. And you have to take care of all of them in order to produce a real number. Then, but the problem is that what they usually do is that, okay, we think that, well, if you have a divergences, okay, make the integral not in 4 dimension, but in d dimension. And then you take the limit when the dimension comes to 0. This is one of the ideas in dimensional regularization. However, we live in 4 dimensions. How we handle this infinity when you take the limit to 0. So there are two methods. There are two methods basically in the world. So you have dimensional methods when you change the space-time dimensions, and you have non-dimensional methods. When you work in 4 dimensions, you stick into 4 dimensions, but you have to do something reasonable in order to cancel the singularities. And this is what I want to sketch in the next slides. So over the years, you have in the 62, Stoff and Bellman, so dimensional regularization, when you have, you pass from 4 to d dimension, and then you compute everything in d dimension, and then you take the limit at the end of the integral, when you compute already the integral, you take the limit, the dimension to 4. You have conventional dimensional regularization. It is basically more or less the same, no more. They have some subtleties. Each one has some subtleties. You have dimensional reduction. You have 4-dimensional helicity in the 90s, and you have the 6-dimensional formalism, and you have the 4-dimensional formalism. But all of these ideas stick. They try to do the computations in other dimensions than 4, and then you try to take the extrapolation to 4 dimensions by some means. What are the things that you have to take care of when you do integrals in more than 4 dimensions? So you have to find some mathematical consistency in all of the ingredients of the algebra, for instance. You have to add, you want to have unitarity and causality, as the previous speaker was saying. If it's possible, you can add some symmetries, and also you would ask for computational efficiency. So what is dimensional regularization at work? So you have this integral in 4 dimensions, you have an integral in 4 dimensions, and what you do is just only to change the dimension to 4 to d, and then you do the computation in d dimension. So what you do with the metric, so if you ask for the metric, you have to, if you start from S4, this is strictly in 4 dimensions, you can go into quasi-d-dimensional space, and also which is contained into this in this S4, and then this is quasi-dimensional, but ds-dimensional. You have, this is very technical, but all of the ingredients. You take the metric in d dimension, but you can also take for vector fields, singular vector fields, you can take all of them in d dimension. But for regular vector fields, you can ask some of them in d dimension, some of them in 4 dimensions. And this is the mathematical consistency that I was saying. At the end of the day, what we use nowadays is dimensional reductions, because this contains all of the rest. So it is a path that over the years has been taken, and now this is a very nice method to compute the observables. And for instance, what I was saying to you about these consistency checks. So if you have, for instance, this Feynman diagram, you use Feynman rule, you have the vertex, the propagator, the vertex, the propagator, and then you have here the G mu nu. At the end of the day, you're going to have 5 gamma matrices, and you have to contract them. You go to the books, to the textbooks, and it will tell you that in dimensional regularization you have this 4 minus ds minus the dimension. In 4 dimension, of course, this will not appear, but if you remove it from the beginning, maybe you are removing also some divergent term that you have to keep in order to cancel other stuff. So this is like I was saying. So for instance, in conventional dimensional regularization of Hoffman-Bellman, the dimension is 4 minus 2 epsilon. But if you go to dimensional reduction, the S is 4 and other stuff. So in some terms, they are going to contribute to the cross section, and in other terms, you cancel them in order to not to keep all the information, spurious information till the end. And then consistent algebra, it is important in the full computation. So what we do, what the previous speaker was saying, is like when you compute, for instance, E plus E minus two jets at next to the inordinate in QCD after some consistent renormalization. I'm not going to tell you all the story, but what I want to tell you is that if you compute this virtual correction, which has divergences, in terms of epsilon, you have it has a particular form, 1 over epsilon squared, 1 over epsilon in these schemes, and this is the Hoffman-Bellman. You can see that the divergences are basically the same, minus 1 over epsilon squared, minus 3/2 over epsilon, but the real numbers are different. I mean, the rational numbers are different. When you add the real contributions, consistent in this approach, then you have the cancellation of divergences, and the rational numbers are different among them. But when you add them all, the real and the virtual, this is one loop. So the results are consistent in both dimensional schemes. In both dimensional schemes, the results are the same. So if you do the calculations, consistent, so the result is the same. So this is something like we like to from these dimensional schemes. So what are the issues? Can we continue on doing the things with dimensional schemes? Why do we need other schemes? So the problem is that virtual corrections sometimes are very hard to compute. At one loop level, you have all this recursion relationship that Andres and Leonardo was saying, so it is doable. But then the real contribution is really a hard task to perform. Then the cancellation of ultraviolet of the infinity energy limit, it is very tedious. Every single scheme you have to do a fine tuning on all these UV terms in order to have the full cancellation. So it's not simple. And also one of the issues is the gamma 5 matrix is not well defined in the dimension. So by construction, the gamma 5 it is like in 4 dimension is like this form. But if you go to D dimension, the epsilon, the Levi beta tensor, you have to do it in 4. And then this is in D dimension because all the gamma matrices are promoted to D dimensions. You can also have another idea. You have the algebraic definition of the gamma 5. And if you ask for the gamma 5 to be 0, like the anti-commutation relationship, so if you stick with this definition or you have this algebraic definition, so the answers are going to be the same, are different. The results are different. So if you want to compute pseudoscalar particles, you are going to have a trouble. Because you have different results. This is an open question also, the gamma 5 up to dimensional regularization. What is the non-dimensional method? Because you have this gamma 5 problem, you have all these, you have to keep track of all these of singularities. They have all other options like implicit regularization, which is very new in the 98, the 4-dimensional regularization of 4-dimensional renormalization in the 12th, the 4-dimensional subtraction, which I am working on that. So that's why I'm going to tell you a little bit more of that. And what we want to do is like to think of the cross-section in 4 dimension, which you need to remove threshold singularities. You can use also ideas of causality of multi-loop amplitudes. You can do also the loop tree duality in quantum computing, what I mean to extract the information by using quantum algorithms. Also, we want also mathematical consistency, unitarity and causality, symmetries, and computational efficiency. So just to have in mind what is happening in the other methods, and then I'm going to pass to the method that I work with. So in implicit regularization, they ask for what is needed, like locality, unitarity, Lorentz symmetry, and then the divergences that they are going to have at the amplitude level, they are going to appear as a base of divergent integrals. So they are going to separate the integrand into a set of terms, and the terms that are divergent, they are going to like put it into some place, and then they are going to ask for the cancellation of these terms. They are not going to compute them numerically, but they are going to know that the divergences is going to be cast in some integrals, and then they use this renormalization subdivergence by the use of Bogoliubo recursion formula. So the idea for them is like, you know that you have the divergences, you are going to keep the divergences apart, and then you're going to cancel them with other terms. In the FDR, it's also the idea of they know that the amplitudes have divergences, and they are going to stick in 4 dimensions, and they are going to cancel by a replacement rule. And in this replacement rule, you will going to solve the integral, but you are going to do it like by hand in some sense. So you have to do the replacement, and then you see where are the divergences, and then you cancel the divergences by doing some shift in the integrals. And then we are, so what we started to think about it is about the cross-section. If you think about the cross-section is never, it doesn't have any divergence. They have real numbers. So why we need to go into the dimensions if we know that at the cross-section level, all the quantities are real. So what we usually do, as Leonardo was sketching, so you have the leading order, you know how to handle this expression. You have the next to leading order when you have the virtual, as I show you, and the real contribution. So the problem in these ideas is that if you think this quantity, which is in the virtual, it has some singularities, and the real has the same singularity, but with the opposite signs. But what if we find a way in order to put all these integrals into a single integral? So where all the integrands you shifted in some way, and then you don't need to go into a d-dimensional space, because remember that the d-dimensional space is needed in order to perform the integrals with divergent integrals. But if you think at the integrand level, if you merge these two integrands, they will not have infinities in there. So you think that if you find a way to merge these two, so then you don't need to go into the d-dimensional space. So that's the basic idea of why we would like to not go into the dimensions and how we are going to do it. So this is the path of the loop tree duality of the 4-dimensional subtraction. So in the 2008, we have the loop tree duality, then the application of the loop tree duality into a quantum field theory in 4 dimensions was done in 2014. And then here they use the loop tree duality to a real process to cancel the singularities. Then they have this the analysis of the singular structure, and the two-loop numerical approach was done in the 15, and in the 20, and then the multi-loop analytical result, we know how they look like now. Then the geometry and causal representation, and then the automation and the UV cancellation has been already studied in recently last year. So what most of my work has been done in this loop tree duality thing. So I'm going to sketch more or less what is this, the loop tree duality thing. We know that in the quantum field theory, whatever quantum field theory, it doesn't matter. Always the problems are in the denominators. So the denominators has the divergence. If the numerator is whatever rational function, whatever polynomial, sorry, so it will not give you any issue when you integrate that. But the problem is when you have this denominator here. So you have two options: or you have, or you compute this in d dimensions, or you try to do something clever in order to reduce the number of integrals in some way. So what loop tree duality does, it is very simple. It is you use the Cauchy residue theorem, and then you set all the internal lines on shell. So here is like you set the pole in the QI propagator, and of course the evaluation of the residues in the other, it will give you a different denominators from the rest of the propagators, which we call it the dual propagator. Having this idea in mind, so if this delta tilde sets a particle on shell, you can think that the virtual is separated into a set of diagrams which have been coded only once at one loop. What is different from the other recursion relationship that Matt was saying? So in Matt, in Matt's talks, you can see that the idea is to cut fully the diagram. You can also have connected diagrams, but with us you cannot have that. In the loop tree duality, you always have trees. You have never have, for instance, into a box for cut it. You always have a single cut, which is the basic, which is the main advantage of the loop tree duality. Then you shift the prescription, and it doesn't matter that. So this is the basic idea. So if you go into the BCF formalism, here you have single cut, double cut, and triple cuts from the triangle. We know also that the infrared singularities are always casted into triangles. The basic, so the most simple one is the triangle. And so if here it means that if you cut the three possibilities of the triangle, you have only three cuts. One of these cuts, you can say that when one of these particles gets on shell, you can have like a mapping in the variables, a change of variables, and then you can add it into the real contributions. And when you add them, then you cancel all the divergences, and you can compute the cross-section in 4 dimensions. This is the basic idea. So here you have the real, so the idea is that one of the particles that you cut are going to be merged into the real one, and then you add for momentum conservation. You ask for momentum conservation. When you do that, then you are sure that the integrand, even if it could be not nice, you know that there are no divergences there. So the Monte Carlo is going to take not too much time. The other divergences that you can have are the ultraviolet divergences. And for the ultraviolet regime, we know that the bubble diagram casts all the information on the ultraviolet. So if you want to cancel the ultraviolet, what we're going to do is like you are taking the limit of 1 Feynman diagrams to the infinity. So the bubble diagram, the scalar bubble diagram, has 2 propagators. So that means that the ultraviolet counterterm that you need to cancel these divergences has to be squared. And because the Cauchy residue theorem holds for higher powers, you can compute the residue of this propagator. You take the derivative and everything into consideration, and you finish with a single term. So it is not. So the algorithmic way is basically the Cauchy residue theorem. That is not hard to perform. We did that in 2016 for the same process like the photon to QQ bar at next to the northern. And what is important is that when you do this algorithmic way, and then you have the normalization procedure also, you can say that you can divide all the information into 3 different pieces, and these 3 different pieces has no divergences at all, which is going to happen with the other dimensional schemes. In the all-dimensional scheme, the real contribution is divergent, and the virtual contribution is divergent. But when you add them all, when you add these 3, you will find the 3/4 CF alpha S over pi that it is founded in dimensional scheme. So it is a different way to find the result, but we avoid these infinities from this merging of the integrand at integrand level of the real and the virtual contributions.
You have 4 minutes left.
Yep. So what is it? What is the now? What we're thinking now? So integrals as sums can be written in many ways. You don't. It is 1. It is 0 plus 1 is 1. 0.5 plus 0.5 is 1. You have a lot of ways to write the same numbers. So we call it the Feynman representation to the Feynman rules. When you apply the Feynman rules, you have the Feynman representation. If you apply the loop triduality, we obtain the duality, the dual representation. But there is also a very interesting point when you compute or when you do some treatment of the integrals. If you do partial fractioning to the dual representation, what is happening is that, for instance, let's before doing that, I'm going to show you some of these multi-loop diagram that we have done in a previous paper. So you have this topology, like they call it multiple banana or sunrise at a loop. We call it maximal loop topology. It's just only 2 points and a lot of lines. Here you have 3 points and all of the differences. 2 loop topologies, not 2 loop, but topologies that you can add without passing to the 4 point, which is the Mercedes-Benz one. So you have the maximal loop topology, next to maximal, and next to maximal. So if you apply the loop triduality, of course you have n lines. That means that you have n minus 1 loops. So you have to integrate n minus 1 times. So it means that one of the lines is not cutted. So it means that you can do the computation, and at the end of the day, you will find this nice representation of the integral. So if you do the same by the Mercedes-Benz, you can find a different representation, but it is also a possibility there is a possibility to find a dual representation of a lot of topologies. What we call it causal, which is the key point nowadays. So when you apply the Feynman representation, you are going to have several threshold singularities. And what is a threshold singularity or non-physical singularity? Imagine that in your denominator, because by combination you can have, for instance, energy components, and one of them is negative. Because you are integrating over from 0 to infinity, the energy component, there is going to be a point in which this combination turns to be 0. And it has to be this, it could be this one, it could be the other one, it could be whatever. When you have one of the sign negative, that means that you could have a non-physical singularity. The physical singularity are the ultraviolet and the infrared ones. What is happening in the causal representation is that if you start from a Feynman diagram, you can always decompose the amplitude in terms of only causal representation, causal propagators. So this is the n to the 3 maximal loop topology. You have 13 propagators, and the whole combination. You can see that if you take the lines, the red lines, you will see that the fluxes of the points are towards the red ones. there are no differences in the sign in the fluxes. So this is important for us because that means that all of the lines has to be aligned in order to have a physical realization of your cross section, which is not happening. Which could be, I don't know, but in the Feynman representation, and because of the loop duality is setting internal lines on shell, it seems that this selection of internal lines on shells is setting also causality for free. So it was very interesting for us. So what is dual versus causal? Imagine that you have this n to the 3 MLT. This is the phase space. We set on one of these phase space to integrate. And you can see that there are these white lines. All these white lines are the combination when you have singularity. These are all singular behavior. If you do a zoom into one of these points, you can see that in the causal representation, in the dual representation, you're going to have a very oscillatory behavior. And in the causal representation, it's very flat. There is nothing. So it's simple. It would be simpler to compute numerically this integral rather than this one. And what the people here is doing is like they are thinking in geometry in order to select the fluxes that can appear into one of the Feynman integrals. For instance, here you have a point, you have a dot, and if you have that one of these is entering, all of the others has to be leaving the fluxes. Or in the other direction, if you are all of them are entering, then the other one has to preserve momentum conservation. There are only two possible on-shell states. By meaning that it seems like you can use quantum algorithms in order to extract all these causal representation, causal propagators in order to have your cross section. So it is interesting that by using the Cauchy residue theorem, the loop duality, you can also reduce the complexity of your integrals by only sticking with the remaining two problems, sorry. So the ultraviolet and the infrared. And so this is the proper algorithm. And then let me conclude. I hope you see that there are a lot of the part of the community working on having precise theoretical prediction for the LHC observables. There are several methods. There are several methods in order to compute, and all of them have their subtleties, and they are crucial to know them in order to apply them correctly. Basically, all of the methods that I show you, they have the same problem: singularities, the identification of singularities, and to cancel all of them in order to produce theoretical predictions. So there are several the loop dualities. This is one of the thing that I have been working on. So they have opened a new window for tackle these physical divergences and physical problems through the causal representation of Feynman integrals. And I think that I'm going to stop here. Thank you very much.
So thank you, Roger, for this now talk. So there is time for questions. So please use your microphone if you have questions. Don't be shy. So I have one, Roger.
Yes.
If I understand well, for example, imagine if I have some reaction or processes, I compute the amplitudes, whatever the method I liked, and then I need to compute the cross section that is a real number. But I have problems with the regularization, the normal regularization.
Yes.
So your method, this loop duality, puts constraint in the amplitude, or just is the method of that how do you remove the divergences in the denominator?
Yes, so it is. So it is interesting the question by itself, because usually you tend, when you study relative corrections and all of these things, you will always have divergences. So it's very interesting to hear somebody saying, no, well, you don't have divergences, no? But divergences are everywhere. So the problem is that if you have, for instance, a denominator, and then you add the contributions together, so what is going to happen is that when you do a Monte Carlo simulation, so the numbers are going to cancel all of them at the same time. You don't need to go into the dimensions, but what is you are going to use at some point, of course, you need to use at some point epsilon dimension in order to constrain or to construct some of the counterterms. However, once you build the counterterm, you can forget everything, because this counterterm is universal. So this is other important feature of the loop tree duality, because all of the particles are on shell. When you cut it, then you do not constrain, in some sense, the integral, but you are separating the integral, your problematic integral, but all of them are problematic, into a set of integrals, and these integrals, point by point, it is local, in that sense that when you launch the Monte Carlo, the singularities are not present there. You can also do the dimensional regularization scheme, and you will have the same answer. But you will see that you do not need the epsilon. You can take the limit to epsilon to 0 at the integrand level, and then your result is finite. But you have to do this. You have to keep in mind that all of the calculations that you are usually used to do, it is more or less the same, but with the trick that the virtual correction, you are going to separate in 3 reals, and these reals is going to match, or 3, or whatever number of real contributions.
So it's really amazing work. So please extend again to Roger.
Thank you very much to everybody.
So our next speaker is Carlos